Now we're going to connect electric and magnetic fields. So let's take a look at this question. An electric field is introduced to keep a particle traveling straight. So we have this particle here that had an initial velocity this way into a field. And this blue line represents the way that the particle would go, or the way that the particle wanted to go, if there had not been an electric field. So that means there was a force toward the center of that circle that's starting to form. So that's the way our magnetic force pushed. Let's look at the questions we're going to ask or answer. What is the charge of the particle? What direction does the electric field point? What is the strength of the electric field? Well, a couple things to note. First of all, if this thing is going to travel in a straight line, it is then in translational equilibrium, and all its forces must balance. So that means that the electric force, not the field, the electric force would have to point up. Now that could mean we have an upward pointing field and a positive charge, or a downward pointing field and a negative charge. But we do know that our magnetic force is going to point down to have this circular motion happen, and then our electric force is going to balance it by pointing it up. So we need to figure out if that's a positive or negative charge. What we'll do is we'll check with the right-hand rule. If V cross B gives us down, we'll know it's positive because the right-hand rule describes what the force a positive would feel. If V cross B points up, that would mean that we're dealing with a negative because the right-hand rule points opposite the force a negative charge would get. So the problem tells me that the velocity is this way, and that the magnetic field is into the page, which is also what those X's mean. And so from my perspective, I'm pointing into the page. You're going to have to kind of consider it mirrored. So into the page with my palm, fingers curled that way. Thumb points down. That means there's a magnetic force down, which agrees with what our problem said. And since the right-hand rule gave us what actually happened, that means we're dealing with a positive. If the right-hand rule gives us an opposite of what happened, we're dealing with a negative. I'm going to do this one more time with the kind of right-hand rule that I told you is very hard to mess up. Vector 1, V, cross B into the page. My thumb points down, meaning that the force is down. And we're dealing with a positive because this matches what happened. If the magnetic force were pointing up, we know this was a negative because it did opposite what the right-hand rule says. But V cross B gave us down, dealing with a positive. So now we know that we're dealing with a positive charge. That also means to get an upward electric force, we would need a field that points up. So let's do this one step at a time. So for part A, we have a positive charge. For part B, in order to get an upward electric force on a positive charge, we would need an upward electric field. So E points up. It's E. And C, what is the strength of the electric field? Well, since these two forces are the only thing coming into play here, we know we need to balance the electric and magnetic force, meaning for part C, we can look at those two to balance, and we can consider F equals FB equal to, FB, up equals down, because we're in translational equilibrium, it's moving at a constant velocity, one direction, one speed. Our electric force would be given by, so remember we're looking for the strength of the electric field, and that force is given by electric field strength times E, Q times Q, E, so electric force is QE, remember that, charge times field strength. And the magnetic force, since we already know it's perpendicular, we don't have to worry about sign or anything like that, would be given by QV, B. Alright, if I'm solving for strength of the electric field E, I notice that the Q's on both sides, if I divide by Q, will cancel. And I'll get E equals VB. And the problem gives me B, 5 teslas, but it doesn't give me V, so I would have to leave my answer as E is V times 5.0 teslas. And I don't see any way to figure out a velocity given either, or any clear path I can see to get to velocity. That is E equals V times 5